喂，这个看能不能挂在我的这边口袋可以吗？可能要调一下。Hello Hello，喂喂喂喂喂喂，哎，这一间如果不用麦克风可以吗？
不用应该也可以，如果你声音
因为我觉得用麦克风，我怕到时候如果它远近的话，声音会不太好。对啊，
或者是说我们有手拿的麦克，
手拿那个也不太好，因为我
你要找出去。
因为我左手想要去做别的事。
那这样好了，其实应该，不过这样会不会影响到那个连
对啊，
线？
我是怕另外一间。
连线那边就会比较不清楚。
对啊，我是怕另外一间。那不行的话，我就用这个好了。
其实你，要不然就是说你把麦克风放在固定的位置，就是
对啊，
不要
就是挂起来，这样子。喂，但是我有转头，是不是又歪了？这个我头就不能转了，我这样子，就是对啊。
其实如果不会发生那种很大的爆声一下，
喂喂喂，呀，这个是比较讨厌一点。
得到讲者，就是只能看到这个地方的话，是没有办法看到下面。
看得到整个讲台，看不到下台。所以我站在这里，他看得到吗？确定，应该是可以。OK， 好吧，没关系，没关系。喂 ，OK。怎么前面都没有人坐？哦，太高了，太高了。
好啊，那各位通讯组的同学哈，请陆续就座哈，我们那个演讲即将开始了。那我们今天呢，这个很高兴呢，请到这个黄绍伦博士哈来给我们做演讲啊。那黄博士呢，他是在这个麻省理工学院毕业的博士。那之后呢，他一直在从事着 information theory 以及他在这个data science 还有跟 machine learning 上面的这个研究哈。那今天我们很高兴请到他来演讲啊。那我们是不是掌声欢迎这个黄绍伦博士的演讲
？OK， 后面听得到我的声音吗？都可以哈。OK， 好啊，那谢谢博清，这个一个很好的介绍。OK， 那我今天没都习惯用英文嘛，是不是 ？OK，so I will use English. Okay, let's start. Okay. After introduced by Shannon 70 years ago， 这个好像不是很好吧。喂。Okay, after introduced by Shannon 70 years ago, information theory has been a nice and popular subject for several decades, and it has been used quite a lot in digital and wireless communication systems. Well, in general, what makes a theory so nice is that once the theory itself has been developed, it can be used to talk about many different kinds of things. Well, actually, information theory is this kind of theory because information theory explains how information is exchanged in all stochastic process. So information theory itself, this theory itself, is much broader than just the coded transmission. It's much broader than just the coded transmission, but can be used in many different areas. But the current research trend of information theory is still mainly on the communication-related problem, so there leaves a great potential to apply information theory to study different kinds of scientific problems. Well, then what will be the next big shot for information theory? Well, let's look at these pictures. Because of the fast growing of the internet and the mobile devices, there are tons of data generated every day. For example, there are many active users in the PTT to read and post messages every day, and so do the Facebook and the Twitters. In addition, the online shopping such as the eBay and Netflix have also attracted many attentions and has become important elements to our daily life. So many different kinds of data, such as the comments to the social issue and the trading records of online shoppings, are generated every day, and how to efficiently and effectively analyzing this big amount of data has become an important issue to the current world. So in this talk, we are going to introduce an information-centric approach, which uses the information theoretic ideas to address the big data analytics. Well, before going through the details, let me first introduce some practical examples to motivate our approach. Well, the first example is the Netflix problem, where we have some records of the user watching some movies, and the goal is to know the correlation between the users and the movies. Specifically, in this problem, we have two data variables, x and y, where the data variable x means the user ID, and the data variable y means the movie ID, and the data pair x, y in this Netflix data set means a user x watches a movie y. In addition, in this Netflix problem, each user x will give a rating to the movie y he watched, and we model this rating as the number of times this data pair x, y appears in this Netflix data set. For example, if a user x give a movie y with 5-star rating, then we assume this data pair x, y appears 5 times in this data set. Well, this is to give more weighting to the user who likes a movie. Okay, moreover, in this problem, we ignore the timestamps in this data set because the watching time, or the older the user watching the movie, is in general less relevant to his preference about the movies. Okay, now in order to find the useful features to characterize the users and the movies, we want to design an algorithm to extract m-dimensional signatures from the data samples. Well, specifically, we want to design an algorithm to assign each user and each movie an m-dimensional signature functions such that this signature function is good to describe the users and the movies. For example, if a user likes a movie, or if two movies are in the same category, then their signature functions should somehow be similar. Well, so the question here is how to design the good algorithm to find the useful signature functions such that two similar movies can have similar signature functions. So in this problem, we want to design good signature functions to extract useful features from the data, and this idea of using the signature functions to extract useful features is actually widely used in different machine learning problems. The other example is this NtuEE70th digital recognition problem, where in this problem we have some handwritten digits, and the goal is to know the label of these digits from the image pixels. Well, in this problem we also have two data variables x and y, and here the data variable x means the label of each image, and the data variable y is the image pixels. Now we want to design the good signature functions such that we can recognize the label of each image from the good signature functions. In general, we should have trained all these image pixels all together to find a good signature functions. However, in this problem, each image has a size of 28 by 28 image pixels, and the complexity of training all these image pixels together is just too high, and it's practically not doable. So a practical approach is to divide each image into sub-image blocks, and then we train the signature functions for each small block, which is how the neural networks typically do. So in this problem, we would like to divide each image into overlapping sub-image blocks, and each small block has a size of 6 by 6 image pixels, and then we want to design the 4-dimensional signature functions for each sub-image block. Once we have a good algorithm to design the good signature functions for each sub-image block, we can stake all the signature functions from each sub-block of one image as a vector associated to this image, and then we can apply the linear support vector machine with this vector and the image label to classify this whole bunch of images into 10 groups, and then we can recognize the digits. And then the key question here is how do we design the good algorithm to find the really useful signature functions for recognizing these digits? Okay, now if we look at both the Netflix and the NtuEE70th problem, well, we know both of them have the strong existing solutions. For example, in the Netflix problem, the collaborative filtering works well for the recommendation systems, and for the NtuEE problem, we know the deep learning and the convolutional neural networks have very good performance. However, if we look at both the existing good algorithms for both problems, well, they are actually very different, which means a good algorithm for one problem may not also be good for the other problem. So in this talk, we're going to show an algorithm that works well for both problems. Actually, our approach is very general, such that many different kinds of problems can be solved by the same algorithm. Okay, then how do we find such solution? The main difficulty here is how to choose the right algorithm to reduce the high-dimensional data into low-dimensional but good signature functions, which is known as the dimension reduction in machine learning. Well, actually, there are also many existing approaches for dimension reduction in machine learning. The most widely known approach is the principal component analysis, the PCA, which wants to extract the principal component of the data from the singular value decomposition of the data matrix. Well, in general, the PCA extracts the linear features of the data and is theoretically optimal if the data are jointly Gaussian distributed. However, the PCA cannot extract nonlinear features, which are very important in many problems. For example, in the NtuEE problem, the error rate of recognizing the digits by only using the linear PCA is about 15 to 20%, which is practically not very good. So in order to extract nonlinear features, there are also many approaches such as the manifold learning and the neural networks and deep learning are developed for nonlinear dimension reduction. In particular, the manifold learning reduces the high-dimensional data into low-dimensional embedded manifold to extract nonlinear features, and this approach has a very strong mathematical insight behind. On the other hand, in neural networks, the data are mapped by a specific feature function such as the sigmoid function to create the hidden layers and extracting the nonlinear features. And we know these neural networks have a very good performance in many problems. For example, the AlphaGo, which is the hottest news in these days. However, if we look at these two approaches, the manifold learning and the neural networks, well, there's actually no clear connection. There's no clear fundamental connection between these two approaches, such that we can compare one approach to the other approach. So there seems to be a disconnection between a good theory and a practically good approach, such as the neural networks. So in this talk, we are trying to establish this kind of connection by using the ideas from the information theory to find the good signature functions for extracting useful features in engineering problems. Okay. Now here is the idea of our approach. Suppose that we have two data variables, x and y, where the x is the data that contains useful information, and y is the observation, which can be viewed as a noisy version of this x. For example, in the NtuEE problem, this x is the label of the image, and y is the sub-image blocks that are used to infer about the labels. In addition, we want to write the empirical distribution of x and y from the entire data set as px and py. So these px and py are the empirical distribution when you look at the whole data set. And the joint distribution between the x and y can be specified by a conditional distribution py given x, which can be viewed as a communication channel between an input distribution px and an output distribution py. Okay, now we want to make an important assumption on the data samples of our data set. Here, we want to assume that the data samples in our data set is permutation invariant, which means we don't care about whether a data sample appears earlier or later than the other data sample, but we care about how many times this data sample appears in our data set. So we don't care about the order of the data samples in our data set, but we care about the empirical distribution, the empirical behavior of the data samples in our data set. Okay, actually this assumption makes sense in many problems. For example, remember that in the Netflix problem, we ignore the timestamps of the Netflix dataset because the watching time or the order of the user watching the movie is in general less important to his preference about the movies. So the order of the data sample is less important, but the empirical distribution of the data sample is much more important. Okay, now with this assumption, when we observe, when we get a particular data sequence of X, all the information about this particular data sequence of X is contained in the empirical distribution QX of this particular data sequence from the data set. So here we have two distributions. The QX is the empirical distribution of the particular data sequence of X from the entire data set. And this PX is the distribution of the empirical distribution of the entire data set. Okay. Now, if we want to know about the information or the features of this particular data sequence of X, we should look at this empirical distribution QX because we just assume the data sequence are permutation invariant. And this is equivalent to look at how this empirical distribution QX is varied from this reference distribution PX of the entire data set. So all the information about this data sequence is contained in this variation of empirical distributions. Okay. Now let's look at this conditional distribution Py given X. Well, if we change the distribution in this X space from Px to Qx, then the distribution in this Y space will also change from Py to Qy, just like passing two different input distributions through a communication channel. So the variation of distributions in this input space will induce some variation in this output space. And more importantly, some directions of the variation in this input space can induce more amount of variation in this output space than other direction of variation. So in order to quantify this variation, in information theory, we measure the amount of variation in this input space by the KL divergence dQx/Px between the distribution Qx and the Px. Well, this measurement, this KL divergence measurement, essentially tells us about how much information is contained in this data sequence with this empirical distribution Qx. And similarly, we measure the amount of variation in its output space by the KL divergence dQy/Py between the distributions Qy and Py. Now we have the information measurements in both spaces, and we want to know which direction of variation in this input space can induce the most amount of variation in this output space, which means we want to know which direction in this input space is the most informative to this output space. And this is actually an information theoretic problem where we want to maximize the KL divergence dQy/Py in this output space, given per amount of variation in this input space. Well, it turns out that there is a very nice geometric structure if we approximate the KL divergence by the first order Taylor expansion of the log function in this KL divergence. With such an approximation, the KL divergence dqx_px can be approximated as the L2 norm square of a perturbation vector phi, which can be specified by the variation between the distributions qx and px. And similarly, the KL divergence dqy_py can be approximated as the L2 norm square of the perturbation vector psi, which can be specified by the variation of the distributions qy and py. Okay, sorry. Now, what is nice here? What's the nice geometric structure here? Is that if we look at this perturbation vector psi, this perturbation vector is actually the output vector of passing this perturbation vector phi as the input vector through a linear map B, where the matrix B can be found by the joint distribution between x and y. So, so this reduces this information theoretic problem of KL divergence into a linear algebra problem where we want to find the direction of the variation in this input space such that after passing through a linear map B, the output vector has the largest L2 norm square. And then the largest, the optimal direction of perturbation in this input space. And the corresponding output vector is just the singular vectors of the matrix B with respect to the largest singular vectors. And actually, the optimal perturbation vector in this input space tells us about which direction is the most informative to this output space, which means that a direction of perturbation, of variation, can bring the most amount of information in this output space. Now, you would ask, why do we care about which direction of a variation is more informative? Well, the reason is the following. Consider that in a data analysis problem where we want to infer about the features of x by the observation y, if we know the entire Bayesian model between py given u between the observed data y and the objective feature u for making the decision, then we know which direction py given u we should look at about the variation of the distribution and the sufficient statistics to detect the variation along this direction from a sequence of observed data y1 to yn is simply the log likelihood function of this data sequence. Well, if we know the entire Bayesian model, this problem is very easy. It's just a traditional data inference problem. There is nothing fancy here. However, the difficulty here is that in big data problems, both the data variables x and y are very high dimensional data, and we often don't have enough number of samples to learn this model, this py given u, this model, and we don't know what's the right way to reduce the dimensionality of the data such that we can learn this model. So in these problems, we cannot assume we know this model py given u, and we just don't know about what's the log likelihood function in this problem. So in this case, well, what we can do here is to reduce the dimensionality of these data variables while extracting as much information as possible. So essentially, this the largest singular vector of our matrix B essentially tells us about the most informative direction in this input and this output space, which keeps the most amount of information in this output space. And the feature corresponding to the direction, the optimal direction of perturbation, of variation in this input space, is the most informative feature that can be extracted by the observation data. Okay. Now given a sequence of observed data, y1 to yn, if we observe this data sequence, and if we know what's the objective direction qy that we want to look at about the variation of distributions, then the amount of variation of the empirical distribution along this objective direction qy can be detected by the log likelihood function on this observed data sequence. This is a traditional approach. Apparently, we can do the sufficient statistic and the log likelihood function. Okay, now if we look at this log function, well, this log function actually extracts all the relevant information in this observed data sequence about the variation along this objective direction, which is often called as the score function in the computer science. Well, if we make a simple approximation of this log function, we can write this score function as a weighted variation between the distributions qy and py. And then the evaluation of the score function essentially tells us about the amount of variation of the empirical distribution of this observed data sequence along this objective direction. And actually, this score function is very important because it tells us how to reduce the dimensionality of the data, which can be viewed by a geometric picture. Here, suppose that we assume that this empirical distribution of the observed data sequence y1 to yn is p hat in this space, and this phi is the perturbation vector corresponding to this empirical distribution p hat, basically corresponding to this direction. And then all the information about this observed data sequence y1 to yn is contained in this high-dimensional perturbation vector phi. And the amount of information contained in this data sequence is simply the L2 norm square of this perturbation vector. Well, now in order to detect the amount of variation of this distribution p hat along an objective direction qy, we will evaluate the score function g on this observed data sequence. And it turns out that this computation is mathematically equivalent to compute the inner product between this perturbation vector phi of the observed data sequence and the vector psi, the perturbation vector psi of the direction of the score function. So the evaluation of the score function is equivalent to project this perturbation vector phi onto the direction of the score function and then measure the projected component. And then the largest singular vector of our matrix B essentially tells us about which direction is the most informative that we should project this high-dimensional perturbation vector to reduce the dimensionality. And the evaluation of the score function tells us about the information of the most informative feature of the data. So the score function, well, essentially reduces the dimensionality of this high-dimensional perturbation vector into an informative, a real number, which can be further applied to deal with machine learning or signal processing tasks. Actually, this picture is very important because this is how we go beyond the traditional information theory. Well, in traditional information theory, we care about the total amount of information in the data, but we cannot differentiate which part of information in the data is more important than the rest part. So if we look at this picture, we just don't know which direction is more informative. We should project this perturbation vector to reduce the dimensionality. We just don't know. From traditional information theory, we don't have a sense to do this thing. However, well, on the other hand, our approach tells us which direction in this space is more informative, and we know how to reduce the dimensionality of this high-dimensional perturbation vector by evaluating the most informative score functions. Okay, now in addition to the information theoretic interpretations, well, the score functions from the largest singular vector of our matrix B also has a strong connection to both the statistics and the signal processing. Well, in statistics, there is a measurement called the HGR correlation, which measures the correlation between two random variables in their functional space. Mathematically, given two jointly distributed random variables x and y, the HGR correlation wants to find the normalized function f and g such that their correlation is maximized. Well, it turns out that the score functions from the largest singular vector of our matrix B is precisely the optima functions f and g for the HGR correlation. So this actually means that our score function g of y has the high correlation to some features of this data x, which can also be interpreted as that this score function g of y has the high predictive power to some perspective of the data x. This gives an engineering interpretation to the score function. In addition, the largest singular volume sigma 1 of our matrix B is precisely the HGR correlation rho, which connects the information theoretic measurements to the statistical correlation between random variables. Moreover, from the signal processing point of view, we may want to select the feature functions f and g such that the mean square error between these two feature functions is minimized. Well, this is an MMSE problem, a very typical signal processing problem. And it turns out that the optimal feature functions f and g for the data variables x and y are, again, precisely the score functions of the largest singular vectors of our matrix B. So this means that our score function is actually not only information theoretically interesting, but also have the deep insights in both the statistics and the signal processing. Now, how do we compute our score functions from the data samples? Well, apparently we can just compute this matrix B from the joint distribution of x and y, and then compute the singular volume decomposition of this matrix B. But in big data problems, the size of this matrix B is in general very, very huge, and the complexity of the SVD of our matrix B is very high and practically not computable. On the other hand, the largest singular vector of our matrix B can be computed in a more efficient way, which is known as the power iteration algorithm. Well, in this algorithm, we start from a perturbation vector psi, and then iteratively compute the matrix multiplication B transpose times psi and B times phi. And once this algorithm is converged, the output is the largest singular vector of our matrix B. Okay, now we want to transfer this power iteration algorithm to an algorithm for efficiently compute our score functions. The key step is to observe that this matrix multiplication for this B transpose times this perturbation vector psi is mathematically equivalent to the conditional expectation on the score functions. This is a very it's very easy to verify this equivalence from simple math. So we can come up with an alternative conditional expectation algorithm which iteratively compute the conditional expectation on the score function, and the output is the optimal score function we want. Now, how good is this S algorithm? Well, first, the convergence rate of this algorithm is exponential to the ratio of the first and the second largest singular value of our matrix B. So the convergence rate is exponentially fast. In addition, the time complexity of this algorithm is clearly linear to the number of data samples and the number of iterations. So it's linear and it's very efficient. Finally, we want to know how many samples we need to accurately compute the HGR correlation and the score function, which is known as the sample complexity of this algorithm. Well, the issue of the sample complexity happens because in practice, we can only compute the empirical conditional expectations from the data samples, and the empirical mean may deviate from the true value due to the large deviation theory. So in practice, it will be useful, for example, if we know how many data samples we need to accurately compute the HGR correlation and the score function with high probability, which gives a guarantee of the robustness in the engineering problems. Well, actually, we have a theory about the sample complexity. The key message here is that the number of data samples we need to accurately compute the HGR correlation is inverse to the square of the correlation between the score function of the HGR correlation and is proportional to the variance of this correlation. Okay, now remember that in HGR correlation, the corresponding score functions maximize this correlation. So in general, the HGR correlation only need a rather small number of data samples to accurately compute. Well, here is a practical example. In the Netflix problem we just mentioned, we only need about 200,000 less number of samples to compute the HGR correlation, then compute the entry of the joint distribution between X and Y. So this actually means that the HGR correlation and the score function is not only informative, but also very easy to estimate from the data samples. Okay, now remember that we get the optimal score functions from the largest singular vector of our matrix B. Well, we get one optimal score functions. Actually, we can also get multiple score functions from the rest singular vector of our matrix B. In particular, this can be formulated as a signal processing problem to successively select the feature functions, the score functions Fi and Gi, where the goal is still to maximize the correlation between the score functions Fi and Gi, but subject to an extra constraint that all the selected score functions Fi and Gi are uncorrelated to the previously selected score functions. So this guarantees that different score functions are carrying uncorrelated information, and there is no redundancy between the score functions. Well, it turns out that the top n pairs of the score functions Fi and Gi selected in this signal processing problem are precisely the singular vectors of our matrix B with respect to the largest n singular value of this matrix. So this means that we can get the top n pairs of optimal score functions Fi and Gi in this problem by the singular value decomposition of our matrix B, which also reduces the data into n-dimensional signature functions. In addition, well, the selected score functions in this signal processing problem also decomposes the feature space of the data variables X and Y into a sequence of orthogonal functions, which is optimal in the sense that if we want to get whatever n score functions of the data Y, and we hope to take as much information about this data X as possible, then the optimal m score function is precisely the top m score function selected from this signal processing problem. So this means that the score functions from this problem provide a fundamental trade-off between how much information we can extract from the data and how many score functions we need to take from the data. Okay. Now we can also extend the ACE algorithm to compute the multiple score functions. Well, the first step is still to start from some signature functions for both x and y, which can be represented as a matrix F. Well, in this matrix, the role of this matrix means an m-dimensional signature function on a value of x. So this row is an m-dimensional signature, and the column vector of this matrix means a score function on different values of x. So we can write this as a matrix F, where the row and the column has the interpretation of the signature and the score function. And then we can apply the conditional expectation to update this signature G by the signature of F, which can be viewed as multiplying our matrix B to the score function of this F. And similarly, we can update the signature G by multiplying the matrix B transpose to the score functions of this G. And then after the conditional expectation, we need to whiten the signature functions to guarantee that different score functions of F are uncorrelated. And this is implemented by the Grand-Schmidt procedure, which orthogonalizes the column vector of this matrix F by the singular volume decomposition of the matrix F transpose times F. So by iteratively running the conditional expectation and the Grand-Schmidt procedure, we can get our desired multiple score functions. Now let's get to a more interesting part. Well, we want to apply our algorithm and the signature functions to the practical problems. First, we look at this Netflix problem, where in this problem, the data variable x means the user ID, and the data variable y means the movie ID, and the data sample means the user x watches the movie y. So in this problem, we have a bunch of data samples x, y, and then we can apply our algorithm to compute the signature functions. In particular, we assign each movie ID, each y, a 200-dimensional signature functions, and we hope this signature function is good, such that different similar movies can have the similar signature functions. Well, if we run this our algorithm in the true Netflix data set and look at the signature functions, it turns out that this is true. For example, if we look at one Star Trek movie, and we look at all those movies with the closest signature functions to this Star Trek movie, it turns out that those movies are also the Star Trek series of movie. They are in the same category, and they are very similar. In addition, if we look at a Disney movie, and we look at those movies with the closest signature to this Disney movie, it turns out that they are also Disney movies. They are just in the same category. So this means that our signature function actually captures some important features of the movies in this Netflix problem, which means our signature function is useful. We can use these signatures to recommend the user about the similar movies. Now, an even more interesting example is this NtuEE70th data recognition problem. Well, in this problem, the data variable x is the label of this image, and the data variable y is the sub-image blocks. Okay, in this problem, we divide each one image into 64 overlapping sub-image block, and each small block has a size of 6 by 6 image pixels. Okay, and then we can view each pair of sub-image block and the corresponding image label as a pair of data samples xy. And then we can apply our algorithm to assign each sub-image block a 4-dimensional signature functions. Well, then after running our algorithm to assign the signature functions to each small block, we can stack all the signature functions in one image into a 256-dimensional vector associated to this image. And then we can run the linear SVM with this vector and the image label to classify this whole bunch of images into 10 groups and recognize the digits. It turns out that with our approach, well, the error rate of recognizing the digits is only 2.4%, which is comparable to the neural networks with 2 layers. Actually, this result is very good. It's exciting because remember that in our approach, we only map the data by 1 layer, just by 1 layer of the signature functions. So we only create 1 layer, but we beat the neural networks with 2 layers. Now, the reason why our approach works well in this MNIST problem is the following. Suppose that, look at this picture. Suppose that this y1, y2 to yn are the sub-image block of an image, and this x is the image label. In general, if we want to solve this problem, we should have trained all these sub-image blocks together to capture the correlation between sub-image blocks. However, in general, this complexity of training all these sub-image blocks together is just too high and practically not doable. So instead, we want to first forget about the correlation between the sub-image blocks, and we want to first reduce the dimensionality of each sub-image block by a low-dimensional signatures, and then we operate on these low-dimensional signature functions, and we train a joint function of these low-dimensional signatures to capture the correlation between the sub-image blocks, and we train a joint function. Actually, this is precisely how the neural networks do, except that in the neural networks, these low-dimensional signature functions are selected by the specific feature functions such as the sigmoid functions. On the other hand, our approach chooses the most informative functions, the most informative low-dimensional signature functions from the general functional space. So we are allowed to choose general functions. And it turns out that by mapping the data with 1 layer of our informative signature functions, we get the error rate of recognizing the digits with only 2.4%, which is comparable to the neural networks with 2 layers. It's very good. So this means that, well, our algorithm is actually very good at choosing nonlinear functions to capture the correlation between the sub-image blocks, because when we reduce the dimensionality of each sub-image block by a low-dimensional signature function, their correlation are still well captured. We didn't lose the important correlation when we reduce the dimensionality. And our approach is actually very good at combining the information of the data. Okay, well, in addition, our approach is, well, actually very general, which includes different domain knowledges and can be used to many different kinds of problems. For example, our algorithm is actually a nonlinear extension to the canonical correlation analysis, the CCA. Well, in particular, this CCA wants to find the optimal linear functions f and g of the data vectors x and y such that their correlation is maximized. If we look at this approach, well, it's precisely the same as our algorithm, except that our algorithm are allowed to choose the general functions, general nonlinear functions in the general functional space. So in our algorithm, we apply the conditional expectation to compute the optimal nonlinear functions, and the CCA can be viewed as projecting these nonlinear functions into the linear subspace. Moreover, our approach is very general, well, can be used to different problems. Here is an example. In the information security, well, a very important topic in nowadays, and the privacy preserving data analysis, we need to keep some sensitive information privately. So if we transfer this concept to our algorithm, this is equivalent to restrict the signature functions to be designed in certain subspace to exclude the private information. So if we look at both the CCA and the information security, well, they are actually posting the computation constraint to our algorithm, which means our algorithm is actually very general and can include many different kind of scenarios. Okay, in summary, well, in this talk, we've showed an algorithm from the ideas of information theory and the KL divergence. And it turns out that our algorithm and the computed signature functions are good to capture important features in engineering problems and have a very good performance in both the Netflix and the MNIST problems. In addition, our approach is very general, which includes different domain knowledges and can be used to many different kinds of data and problems. And moreover, we also explore the theoretical insight of our approach, which establish a fundamental connection between information theory, machine learning, and the signal processing. So actually, our approach kind of built up a connection from the theory to the practice. This is very important, as I mentioned in the very beginning of this talk. Finally, our approach demonstrates a new potential to more efficiently and effectively analyzing big amount of data, which is very important in the current technology. Okay, thank you.
好，因为时间的关系哈，我们可能只能有2到3个问题，我们开放让同学发问。
If you are interested about AlphaGo, we can talk about this offline. Don't need to ask me online. Because everyone asks me about AlphaGo when we present this talk.
Anyone？ 有任何人要提问吗？可以用中文发问，没有关系。都没人要问。那may I ask a question first? Is it in the future? What do you think about the generalization of your method to compete, say, deep learning method like multiple layer? How do you compare the performance of a multi-layer network? Can you compare? How do you generalize your method so that it can be comparable to the performance of multiple layer neural network?
If we look at this picture, well, this is a very simple picture. We just create one hidden layer here. So in this talk, I just say I bit the neural networks. If we both use one layer, the neural network has an error probability of error rate of 5%, and I get 2.4%. This is how, because we choose a good feature functions in this hidden layer. So if we want to compare to, if you want to improve the performance of two-layer neural networks, you can further apply this approach to design the good low-dimensional signature functions for not only one layer but the next layer. So you need to also find a good way to design this joint function or further reduce the dimensionality of these signature functions. And because here I just apply this G as the linear SVM. We can further extend this to the second layer or the third layer, which can be also an interesting research direction in the future.
So you are saying you can apply multiple?
Well, the idea is straightforward. You want to extend this approach. It's very easy, just because all the algorithm, all the conception, information theoretic approach are just very similar, just the same. But you need to think of how to find a good algorithm to extend these low-dimensional signature functions into the second or the third layer. there are still some works, and also in the neural networks, you will feedback the output for the training data. You feedback if you get a function, you get some results in the training data. You feedback this result to adjust the selected feature functions. So this feedback and adjusting I didn't apply in my talk, which is also another way to improve this whole framework.
It's a very nice talk, very very nice. So the result is actually quite impressive because you apply this to a practical problem and you show performance improvement. Very very nice. And I want to comment that you only use a linear SVM, which is very simple compared to neural networks, and you get a similar result. So my question is following. So it seems that your algorithm depends on the joint distribution of x and y. So in practice, I guess you're using the empirical distributions that you get from the data, right? So let me finish my question. So that's my first question. Okay. A second question is, I'm confused by your terminology. So you have a score function and a signature. So what you observe is y, and x and y's are both the data that you have. So but it seems that you only work on the score function, not on the signature functions. So could you clarify on that?
The second question is easier. Well, so what's the correlation between the score function and the signature function? So that's why I draw this matrix. Well, think of this x as a user ID, as each x is a user in a Netflix problem or a movie. It's okay. So a signature means we want to assign a vector to each movie or each user. So here, if we think of m as 200, then we want to this row is a 200-dimensional vector we assign to this movie. X equals 2 is the movie 2. Well, okay. And the score function means a function is one function among these 200 functions. So a signature is 200 different values of these 200 functions on a movie 2. And a score function is one function among these 200 functions. And so if you look at the column, this column is a score function on different values of x. Means this column is a score function on different movies. Is this clear? So yeah, a particular value of x. Okay. Yeah.
So for y, you also have such table.
Yeah, so for x, I have table F. For y, I have table G. Yeah.
So in your Netflix problem, you basically have F and G. So you
Yes.
You reduce dimension, and then you use the reduced dimension F of x and G of y to do machine learning.
Right. Yeah. So the first question is about the empirical distribution of what? Could you repeat it?
So your algorithm depends on computing the conditional expectation of something, right? So in practice, I guess you first run through all the data sets and get empirical distributions of pxy, and then you use that to compute, or what?
So the nice thing here is that if you want to compute this empirical, this conditional expectation, you don't need to know about the empirical distribution. You can just look at the data. You just go through the data once, and you get, because if you want to compute this guy, you just look at when x equals to 1, how many y equals to 1, how many y equals to 2, how many y equals to 3. You sum up all these things, and then you take average among all the number of samples you take. So you don't need to know about the empirical distribution. And the advantage of of skipping the empirical distribution and directly compute the HGR correlation, it's the sample complexity. Because if you want to accurately estimate this empirical distribution, you need a very large amount of data samples, large number of data samples. But if you just compute the HGR correlation from the S algorithm, you need a much small number of data samples. So you don't estimate the empirical distribution, you just run this S algorithm. So it skips this very difficult to estimate the empirical distribution. We just skip it, but we just directly compute the HGR correlation from this algorithm. Is this okay? Thank you.
好，有没有同学要发问？好，那我们就再一次谢谢黄绍伦博士给我们的演讲啊，谢谢他。